Hello everyone, welcome to Group 5 presentation on initiated chemical vapor decomposition. Initiated vapor decomposition is a polymer chemical vapor decomposition method that combines the benefits of CVD processing with the possibilities of polymer materials. Chemical vapor decomposition is a process in which chemicals in vapor phase react with the surface to create a solid film. Different with CVD, iCVD has an initiator that thermally decomposes to form radicals, which are absorbed onto the surface and initiate polymerization. The low energy cost of iCVD holds advantages over other CVD methods because the process can be conducted at low temperature. The objective of our experiment is to learn and use iCVD technique to see how initial flow rate and temperature can affect the decomposition of thin polymeric films. We will use hexyl acrylate as our monomer and tert-butyl peroxide as our initiator. Here are equations. We need to calculate angle of refraction of laser, film thickness changes, rate of decomposition, and activation energy.
First, the substrate must be cut down to an appropriate size of about 0.8 cm by 0.8 cm. This is to be kept constant across the whole experiment. Next step is to clean the stage. First, you must soak it with acetone. Once the acetone has sat for a little bit, you can then scrape the remaining deposition with a razor blade off of the stage. The next step is to clean the glass pane with acetone as well. Any remaining film can affect the interferometer reading, which is later used to calculate the rate of deposition. We then ask the TA to place the filament into the chamber. Then you place the substrate into the chamber, making sure it's centered and that the laser refracts right into the sensor above. The team then measured the distance between the laser and the substrate, and then the height of the laser, which is used later to calculate the angle between the sensor and the laser. The pressure inside of the chamber is then lowered to about 0.150 torr. An inlet of nitrogen gas is then adjusted to maintain this pressure. Next, the power is plugged into the thermocouple, which will help heat up the stage. Once the temperature is reached, you can then open the flow of hexyl acrylate and tert-butyl peroxide and cut the flow of nitrogen gas. The group then waited and let the experiment run until 3 to 5 peaks after the first value were seen in iLab. Once this was achieved, the experiment was then shut down by cutting all flow of hexyl acrylate and tert-butyl peroxides. Valves were then adjusted to allow the chamber to then reach atmospheric pressure. Once the chamber reaches atmospheric pressure, the filament can be removed and so can the substrate. The next step is to get to cleaning.
Here is a graph of our results, with the rate of film deposition on the y-axis and the flow ratios on the x-axis. Unfortunately, we were only able to get usable data from one of our one-to-one trials due to an error with the iLab software. As you can see, there is no obvious correlation between the rate of deposition and the ratio of the flow rates. This could be due to numerous equipment issues that we encountered during our experiment, such as a faulty thermocouple that kept us from being able to get an accurate temperature reading for some of our trials. As a result of the issues that we faced, our data was unreliable, and therefore our results were inconclusive. In order to determine what effect, if any, that the flow ratio has on the rate of deposition, the experiment would need to be rerun, with more trials being taken at each ratio in order to compensate for the inaccuracies that we faced.